My name is Michael Weiss-Malik. A reminder, this video is going out on Google Video, so please save all confidential questions till after the talk. I guess I'll introduce everybody in the order in which I know them. Sitting over here is Noel Gorelick. He was actually my boss for 9 years. We worked on Mars software together. Steve Silverman here actually built several of the Mars instruments and is now working for Dr. Roger Stettner, who started a company in the 90s to build a 3D camera system that they're going to describe.
Okay, well, thank you very much. We're going to talk about a 3D video camera, which basically uses a laser like a normal camera would use, a normal 2D camera would use a flash bulb. And as a consequence, it's sometimes called flash LADAR. LADAR is a short for laser radar. And so as Mike said, I'm the president of the company, and Steve Silverman is actually a very talented systems engineer who can magically turn theoretical ideas into actual hardware that works. Very important person. And then once you've developed the hardware, you have to turn it into something practical, and so you need software. And so we happen to have Noel Gorelick, who himself is a very magical guy, and I think you're going to be shocked and amazed at what he was able to accomplish in just a very few weeks with no sleep. So, I'll start by just talking a little bit about ASC, Advanced Scientific Concepts Incorporated. We're a sensor design and fabrication company. We've been around since 1987. We've developed different kinds of sensors from X-ray sensors to infrared sensors, and now finally we're doing 3D video camera, laser radar sensors. And essentially our claim to fame is that we design things starting from the integrated circuit. Everything that we've ever done has been started off with a cutting-edge integrated circuit. And well, for the 3D flash LADAR, it turned out that first we had to develop our own lasers, and then we had to develop our own optics, and then we developed our own mechanical systems. So, and that's because we couldn't find anything off the shelf that would work. So now we essentially systems engineer the entire camera, from the integrated circuit all the way through to the mechanical system. So what we have is currently a camera which has a focal plane array of 128 by 128 pixels. Now, it could be a great deal larger. It could be 256 by 256 or 512 by 512, but 128 by 128 was a useful design to demonstrate this capability. And we generate 30 frames per second. We could do a lot faster than that, but 30 frames a second, again, was a very useful number, similar to what you would get from a video camera. And so what we're talking about here is something that's very much like a 2D camera, looks like a 2D camera. It has a lens like a 2D camera, but actually creates 3D images. And I'll give you an example of that in the next chart. So what are some of the technological advantages? Well, what's out there that also generates 3D with a laser? And laser scanners are out there. And what they tend to do is to scan one pixel across a region, and pixel by pixel create a three-dimensional image. And now what we're doing is we're generating a 3D image from many, many pixels at one time. For example, the 128 by 128 is 16,000 pixels. And if we go at 30 frames a second, we're generating 500,000 pixels per second. Whereas these scanners are a lot slower than that. And the other thing is that when they scan, they have to take account of the motion of the vehicle, and in addition, they can't take account of the motion of an object that they're trying to see. Well, if you're running 3D imager at 30 hertz, you're going to be able to see birds flying, rockets flying, things like that. And the other advantage is that we can zoom our cameras, just like a conventional optical system. So here's an example. Let me just escape this guy for a second. If you looked at that, the first part of that image was an ordinary visible image. But you wouldn't have recognized that there's so much more information in that image. And this essentially shows you the additional information. This was 6 frames that were stitched together and textured with the visible CCD camera. And not only do you have the 3D characteristics, now this was taken from one direction, but you can measure things. So there's an enormous amount of information that's available with a 3D camera. So here it is. This is what you would see with a 2D camera. This is what you would see with the 3D camera, and in addition, you'd be able to do measurements on it. This is what it looks like without the texturing. And this is taken at 1 kilometer, by the way, in Santa Barbara High School. And it's eye safe, so even though there might have been students in there, we weren't endangering them. And if you went ahead and looked at the range of, say, a flat object, in this particular image, the range precision was about 1.5 inches at a kilometer. And this is what the camera looks like. And it's just as you would expect, looks very much like a two-dimensional camera. The way it works is this is the laser section, and a laser pulse is emitted, and it strikes an object. The pulse comes back, is focused by the received lens onto a focal plane behind the lens, just as in a 2D camera. And we also have a couple 2D cameras. This is a visible camera, and we also use infrared at different times. This section, that's the laser section. The reason it's so large is we have fans in here to cool the laser. So this is an air-cooled laser. And then behind here are the cards that digitize the signal and also provide the power for the laser. This particular laser is a 20 millijoule. I mentioned it operates at 30 hertz. And this camera weighs 12 pounds. Now, we didn't make any attempt to reduce the weight of this system. If you ask, well, you know, what are the relative weights of these various pieces? Well, this lens weighs about 5 pounds. So you can see that this is a very lightweight system with the potential of becoming much more lightweight. Actually, we're really looking at the tip of the technological iceberg in this system. This is just the first prototype of this kind of a camera. One way of thinking about it, to first order at least, is that this is a kilometer. This camera can take images at a kilometer. Say you wanted to take images at half a kilometer. Well, that would be half as much, and if you square that, you get 1/4. And that's roughly how you could reduce the size, weight, and power of these kinds of systems. That's an approximate figure. Of course, you do other things to try to do better than just that factor. Now, here is the direction that we're going. This is a much smaller camera, which does about the same thing from an electronic point of view. And this is the focal plane. This is the 3D focal plane. And in the next chart, I'll show you a little bit more detail what the focal plane looks like. Of course, well, there it is, the next chart. You would need a lens to collect the light and focus it on this focal plane, and you would need a laser to produce the light. But if you were only interested in hundreds of feet, for example, you wouldn't need a 20 millijoule laser. You could use a much smaller laser, and this whole system would be much smaller as well. So let's take a look at that focal plane. What is it? And what you see is that it's composed of what we call a ROIC, a readout integrated circuit, and a detector array. The detector array, light hits the detector array and converts the light to an electrical current. You see these little metal bumps. Well, on the other side of this is a metal bump as well. So the current goes through these metal bumps. Typically, the metal is indium, and then it goes into this processor. Each unit cell has, and these are called unit cells, each unit cell has the same circuitry in it, and it has both analog and digital functions. It has a counter, a digital counter, which counts the light. As the light goes out, when the light leaves the camera, all these counters start. And then when the light comes back, these counters stop individually, depending on how far the object is. And in addition, we capture the pulse shape with the analog circuitry. Now, in this format, we can use any kind of detector array. For example, in the camera on the previous chart, we were using a indium gallium arsenide detector array. And that allows us to use an eye-safe laser, which is our eye-safe laser is 1.57 microns. If we wanted to look underneath the ocean, we would use a silicon detector array. Silicon is responsive to visible light, and blue-green penetrates water very well. So you have a lot of options in this kind of design. If you have a particular light in mind, you just have to have a detector that works with it. Now, what you end up doing is wire bonding from these wire bond pads to the circuit board that I showed you in the previous slide, and that's how you communicate with this chip. And the way information is read out, there's what's called a peripheral circuitry, and that selects an individual pixel and reads the information out through the peripheral circuitry, out of the wire bond, and then onto that circuit board that I showed you. Now, I want to illustrate, there are a lot of functions in this, on this camera, and I'd like to illustrate them by taking an example from your ordinary life, like you're flying around in your own personal helicopter and just happened to see a dinosaur. And so the first thing you're going to want to do is you're going to want to photograph it. Well, I think what you should do is take a three-dimensional image of it. And you might use the hard target mode. And so in the hard target mode, you'd be firing a pulse of broad pulse of light. The light would strike this entire animal, and the first pulse would be reflected from the mouth of the animal, come back, and then you'd get the neck of the animal, and eventually you'd get the entire animal from light hitting it and coming back and tripping our counters, and then collecting the pulse shape and using the pulse shape to give you a high-resolution image. But suppose someone had already captured your animal. Well, then you might want to take a look at if they were treating him well, and take a look through the net. And so you could do that in the camera. If he were close enough to the net, with the way we capture pulses, you could capture more than one pulse, and you could tell you were getting a reflection from the net or from the animal. Or you can also suppress the response, the first response. In other words, you can program the camera to tell you when to turn on the hard target response, and at that range you wouldn't be hitting the net. You would just end up capturing the target, in this case, the dinosaur. Well, suppose it happened to be hiding in the smoke. Well, you really wouldn't want to escape getting that picture, because that might be a unique picture. And so you could suppress the hard target response completely and turn on your samplers at some range into the smoke, and capture the returns from the animal and process that data and create the three-dimensional image also. Now, the reason you want to do that is because you would end up triggering on the exterior of this smoke, and you'd never be able to penetrate inside. So you'd want to suppress the hard target response, and that's exactly what we do in order to see into the ocean. That's the mode of operation for not only seeing through smoke and obscuration, fog, but also seeing into the ocean water. So I'm going to turn this over to Steve, but I just want to emphasize the differences between this sensor and the mechanical systems. Basically, you end up with, and the mechanical systems are not dynamic. They distort images. This flash is instantaneous. Very high data rates in flash LADAR, and can be much greater than our camera. We're registering an entire, in a scanning system, you really have to register, every pixel is individual, and you have to register each pixel individually. And here we're getting an entire frame of data at one time. All pixels are registered automatically, and, but you end up, if you're going to create a panoramic view, you have to register the frames, and that's what Noel will tell you about. The weight, we're much lighter because we don't really have a mechanical scanning system, and the size is the same thing. The scanners are limited in range because of range ambiguity. If you fire a pulse and you're getting a return from a near object, and then you're firing another pulse, and that near object pulse comes back before the second pulse comes back, you don't really know where it came back from, so there is range ambiguity. With respect to two-dimensional overlaying, it's very easy to overlay on an array of three-dimensional data. And again, you can zoom with an optical system. So I'm going to turn it over to Steve now, who's going to talk to you about different applications of this technology. You got one? Okay. Let me unplug you.
Okay. He's got me on one. Okay. Hi. It's nice to be here. We've been having a lot of fun. Like Roger said, he's a mild-mannered physicist who had a great idea and had lousy hardware. Actually, good hardware, but it needed a little bit of packaging and grouping and refinement. And when we did that, we got something like this. This is something that Noel actually helped us with. This is taken from one position. And how many frames do you think are on here?
80.
There are 80 frames, 80 shots of this thing. Basically, turn on the camera, and we just start scanning it around, and then this comes out. This is the Sunken Gardens in Santa Barbara. If you've ever been there, if you're going to go to prison, this is where you get sent to prison from. It's probably the last pretty sight you'll see in Santa Barbara for a while. The nice thing about our system, and looking at the Google sign up there that says at the end of it E equals MC squared, we rely on that C to get our range resolution. So this is a real time-of-flight system. The nice thing about it is single pulse for each 128 by 128 means nothing moves. And I'll show you some examples of that.
That whole scene was collected in about 10 seconds of imaging.
And he did it with this camera, basically by doing this and panning up and down. Some of the other things you can do with this, like Roger said, it's a dynamic framing camera. We were trying to take pictures of somebody throwing a football. We missed the football, but we had some nice cooperative birds flying through the scene. The picture on the left is our test range that's looking out the front, out of our parking lot to our unfortunate neighbors across the street who we've been spying on regularly. Their blinds keep getting closed more and more and more, so it's okay. This is just a flock of pigeons that flew through the scene. This is the 3D data. These are not textured with visible. This is what, and all of the data we're showing you are uncorrected out of the camera. No pixel substitutions. We don't take out any bad pixels. We don't do any smoothing. It's raw data, so you can imagine what this stuff will look like when we get to clean it up. The nice thing about this is you can actually see some of the motion on the bird wings. If you put some color on there, which Noel has done with other things, you could actually analyze motion in flight with a rather crude system. When I say crude, it's only 128 by 128, and the images on those don't look great without the texturing. This is just a shot of it showing that I can rotate this perspective around. This again was only running at about 8 hertz or 10 hertz, and each area image is a full frame single pulse. We wanted to see how people were walking, and this data is about a year old at this point. We took our mechanical engineer, he's also the youngest guy there, and we said, okay, you go out and lay on the ground for a while. And he did, and he was happy about it. And this is a sequence, again, the first one was the perspective of the camera. We can rotate it up. You'll see the things bouncing in and out. It's because this was prior to Noel, and this application auto scales the range. And so the data's not really bouncing, it's the display tool. It's pretty fun to see this, and we have not applied the range to the X and Y and Z, so the perspectives are not to scale. You can see in the background his shadow projected on the cars, on the windows. It's because we bring our own flashlight. Our flashlight lives right here on this camera. It just happens to be a rather exotic one. It's about a 5 nanosecond pulse. It's an air-cooled laser. We had to build it ourselves because we couldn't find anybody that built what we needed. So the 12 of us got together and came up with a laser design. That dinosaur we call Joe, our electrical engineer, and we plant him behind these things. These are Venetian blinds that are obscured. They're probably about 50% visibility or maybe only 30% visibility. Again, if you range gate, since we're not integrating, we're just sampling, you're not knocked out by that first return off the Venetian blinds, so that's why you can see past it. There are other technologies that can range gate, but they take successive pulses. So if he was running around back there, we could tell you what he was doing. The nice thing is you can tell if this guy's walking away from you holding somebody's hand or if he's pointing something at you. It might change your response in that situation. So this is one of the earliest uses that people were interested in for this type of system. Again, here is just the two shots of what you can see. Now I can just leave this camera in this mode. If I know I want to look past the Venetian blinds, I can just leave it in the mode on the right and have the movie run in real time there. Because we have this area array imager and all we care about is return, since we're not integrating, again, if I get any light back to me, I can see it. It turns out fog, smoke, dust, big drops of rain have a pretty good mean-free path to an object and back, which means on any given pulse, I see a lot of the signal coming back. And because it's an area array, we can piece that back together. And the thing on the left is what you'd see if you were driving your car, and the thing on the right is what you'd see if you're driving your car with a little ASC camera attached to it. Of course, your car would be worth quite a bit. And then these are the two shots of it. We also wanted to see how dust was. Turns out that in certain deserts, the sand there is like cornstarch. So we put cornstarch inside of a tent, got a leaf blower. We put a dummy, that's actually a dummy, not a person. Back there, it's a karate dummy. And you can see that you can actually see through extremely dense particulates, which is another fun item. We've also looked through pouring rain, and liquid rain does not, we haven't seen much attenuation at all at over kilometers. Vapor is a little harder to see through than solid water, and that says, well, yes, we can do underwater type of work. This is just if you pull out the contrast on the right, again, no smoothing, nothing done. In this one, we just stretch the contrast. We're still trying to decide if it's me or our optical engineer, whose name is Brad Short, who's 6'4". We flew this little twin otter plane out of Oxnard. We mounted our camera in the bottom of this, and we collected some data flying around. Oh, this is looking straight down. We were only up about 1,000 feet. You'll see It's a little hard to tell, but the things, there's 2 cars parked there. There's a fence. As it gets on the side, you can actually see the profile on the fence, and we were looking down on the top of a roof line. And you can rotate that roof line around. Again, no visible textured on this. This is the 3D all by itself. And then these are just a couple of images. They actually can measure the height of the chimney. You can measure the roof line. You can measure where the cars are. You can see if the guy's violating any codes, or you can see if this were your house, if you could violate some codes and no one would catch you. This was the coolest thing. We were flying over Oxnard Airport, and they do trainings with helicopters. This helicopter was doing touch and goes on the runway. We flew over the top of it. It's off the ground. That's not an error in our algorithm. And that blade on the top is actually in motion. The tip of that blade is moving about as fast as a small missile. So we freeze the blade in flight. This was a single shot, just a single pulse of the laser, and also illustrating it. Now even the visible image, if we put it on here, that blade would be a blur. And this again shows that that blade is actually about that wide. We've measured it. It's about the right width of a blade. So that's a single pulse. That's, no scanner can do that type of work. Now the fun thing for me, hardware guy, I was lucky enough to send stuff up to Mars. There's good and bad things about that. Everything you build has a very finite window of schedule. And then when it gets there, if it doesn't turn on, you get a stomachache. They've all turned on, but still I'm doing a demo. I'm nervous. Is this thing going to work? I hope it does. But these are things that we've played around with. In the upper left-hand corner, you can see one of our early systems. That's a 15-inch laptop screen. On the side of it is a little flash lamp laser. It's about this big. That's about 4 or 5 years old now. Noel says that's the one we should bring and show people. But it's a one-shot type of camera. We can take a picture about every 5 or 10 seconds. This thing is 30 shots a second, and it's not much bigger. So on the left, you can see systems we built. We put some in gimbals. We have the camera I'm demonstrating here. We have breadboard cameras. We actually build the electronics ourselves. It's really cool in this place. We design the chips. We design the circuit boards. We do the layouts. We specify the parts. We grab a bag of parts. We send them out. They get stuffed. We test them. We get their chips hybridized somewhere. We wire bond them onto the boards ourselves. We design our own optics. We get the glass in. We design the metal. We get that. We put it together. We design our own lasers, our own laser illuminators. We put all that together. And from that perspective, it's a really fun mix of people there because I've got all the disciplines. And I'm a systems engineer, so I like it. I don't have to be an expert. I just get to put it together. This is what happens when you put it together. You get a nice, reasonably compact design. It just runs into a frame grabber interface. We use a couple of little Kensington power supplies, 2 basic laptop power supplies that runs the whole thing, laser and camera. And this camera is 1 watt. So it's not like a processor in your computer that's running at whatever they're running at these days. I'll be wrong tomorrow. It's running at about 450 megahertz, but it's a watt. You can't even tell it's on. The fan noise you hear is just cooling the laser so we can run it at 30 hertz. If I ran it at 5 hertz, I wouldn't have to have any fans at all. I can air cool it. Before I get on to Noel's stuff, I'm going to switch the monitor cable over to here. I'm going to show you a picture just looking down the hall, and then Noel will show you what we did yesterday running around. It was very cool. Google let us run around on the roof and take pictures of their campus. That's an unusual event. So let's just switch this over. And this is the nervous part. Can I find the plug? Okay, 1 down. And now I got to do this monitor. Hello.
Guess it's my turn.
It might be your turn. Well, it did it on the yellow monitor. I don't see it seeing it. It's not projecting.
Please note your screen resolution is set to 1024 by 768.
Oh, the screen resolution is too high. Why don't we jump to your stuff? Probably the best thing, if you come up afterwards, I can show you the camera operation on this monitor. I can tell you about it, though, real quickly. The camera boots up essentially instantaneously. With this laser, 14 millijoule laser down here, this is the laser part, laser power supply, interface board, camera. This camera stopped down to an aperture this big. So in theory, I can take that lens, make it about that big, stick it on that little handheld camera, and I can take pictures of exactly what Noel has shown you. This is the configuration we used all day yesterday. If I want to go further, I can just open up this aperture. Everything worked but the projector, so I'm sorry about that. But come on up afterwards and we'll show you the camera operating. You want a hand?
You can change the resolution on the screen to 1024 by 768.
Yeah, I might lose my control window though.
All right. Hi there.
It was up on this monitor. It worked on the yellow monitor with that same screen resolution.
So we ran around yesterday and collected, I don't know, 10, 15 scenes. Here's some data from it. How much This isn't actually a sales call. This is kind of, I came here and I got to work with you guys, and it was pretty cool. And when I get to go work with these guys, this is pretty cool. And I thought, hey, I know a lot of guys that think this is cool stuff.
This one?
At some point, this demo's going to crash.
This top one? Okay.
But cool stuff, and I'm going to show it. All right, so this is. This is right in front of No Name Cafe. If we roll it around, you'll kind of see what it is. This is a couple hundred frames stuck together. And from this perspective, it's what we call camera perfect. This is exactly what the Viz camera saw stuck on our 3D pixels. And you can't really tell it's 3D yet. Zip around here. And we will see what we can do here. So yesterday there was some kind of carnival thingy going on out there. There's the tents. There's the Google logo up there. You know, you can see a nice square feature on this building. This software is about a week old. I wouldn't even call it alpha yet. So nice ground down here. Zoom around. The trees kind of caused some problems with visibility. Let me go back here for a second. We'll zip back down to the ground. Zoom around to here. I'm actually, let me back up one more step, kind of get the whole view here. I'm leaning sideways, so this is probably giving you guys all kinds of seasickness here. All right, I really am going somewhere with this, honest. So the software has a flashlight mode where you can see individual frames painted in. That's each individual frame as we took it. They're registered together. I'm heading over here to the sign. There we go. That's what I wanted. So we can zoom in on this guy, pan around on him, stick our axis over there somewhere near it. So there's the back side of the sign that we couldn't see. And so it got said 2 times. I made both of them say it
totally raw data. I mean, I'm literally taking the data straight out of the camera and throwing it in a 3D viewer. So the cleanup that can be done on here is phenomenal. But we took this 12 hours ago or something like that, and then so we go back into flashlight mode and we see the other frames around it, and get it somewhere we like it. You can actually kind of come around here to the tree. Well, we'll go back this way. And then we'll end flashlight mode here in a second as we back up all the way. And so there you go. Our pixels our IR pixels are, well, there's 128 of them. The Viz camera we've got on here is a 512 camera, so there's literally 4 times the number of Viz pixels as we have IR pixels. And so we can make use of that. This dunk tank thingy here has a sign on it that we can kind of read, even though there's only a couple of IR pixels on this. The bars on that cage are really thin, but because they're all textured on, you get a lot more detail than the IR camera really has, and so you get some pretty cool looking scenes. There's a guy standing in here. Maybe it's one of you guys. Nobody I recognize. He's a little far away. So that's kind of one data set. I'm going to show you another one now. That's how raw it is. It's reading directly from the camera file when it does that. So, alrighty. Oops, same scene. Wrong one. Up here. Sorry. My bad. Alrighty, so this is one of the ones we took from the roof. Same deal. When it starts off, you're in camera perfect mode, but you can zoom in pretty much anywhere. One of the cool things about this camera is that it sees through all kinds of stuff. So if your office happens to be in the second floor of 43 right there, we were watching you yesterday. You can see the tents. I think those are the tent roofs in the building. This is not the ideal solution to see what I'm doing here. So stick our rotational axis down there somewhere and kind of play with it. So we were hoping to get a full 3D map of the quad. Frankly, the software is not that far along yet, but it's pretty cool. All right, so one more. This one actually kind of demonstrates the 30 frames per secondness, and that's really the novel part about this camera. You can take some stereo cameras out there, you could take a scanning LADAR, get a nice map of the building. People will do that for you. This is different. So this was, I don't know, we were 300, 400 feet away from the gantry right here. Yeah, this one right here. The long gantryway. Anyway, so there's a guy rolling a mail cart through. We'll run him backwards for a minute. And it was a couple more people right after him. And so you can actually, we're looking through this building. We can kind of map the inside of this building, go through the back wall back here. We've got range on this back wall. If one of you guys had stood up, we'd see your head. So, it's just cool stuff. And we weren't even running at full rate here. This was 10 hertz, so we can run at 30 frames a second if you had need. And we have just a real general purpose lens on this. We were photographing from the roof and the high, everywhere we could. So at one point we just pointed at this wall and took a picture. If we were actually trying to photograph people in here, we'd use a much higher resolution lens. We'd have gotten much smaller, finer pixels on that thing. And you know, so you can see, I thought it was cool. I thought you guys would think it was cool. So that's my demos. I got 12 more if anybody's interested, but you know, it's the quad and other people. So I think that's our talk. You gonna hook up?
Yeah, let's try it.
All right, one more try and see if we can hook up the actual camera here.
Okay, we actually, looks like it's gonna work. So.
Anyone want to volunteer for a 3D photo?
Will we be recording it?
Yeah, we can save some.
Yeah.
Okay, let's see if we can get up there now. Should do it.
I don't know if that's a serious question or not.
We'll take you. Actually, go stand by the mailbox.
Still not. There it is.
Yay! Oh, look, we got him.
Standing over there, that's an old picture. Let me just take one. The way this works, I'll just start running pictures. That's live, and you're going, okay, well, why can't I see them? Well, I can do that. I can put shoes on too.
Nah.
So this is that slice mode. I said we capture slices. So in that slice mode, I'm going to start with slice 1, and I'm going to step through. And if you watch the ground, that's the cool part. This is a single pulse from a laser, and you can see that pulse moving. So if you ever, you know, Star Trek, okay, I watched it. I still do. Photon torpedo, right? There's nothing in space to scatter the light back, so all right, you can't see a photon torpedo. But if you had scattering media out there, and you could have had one of these cameras, you could see this blob, a 5-foot blob of light moving down the hallway, and that's what you're seeing. Okay, now if I take that, and I take that blob of light, and I know the time to it, I'm not doing it live, but I'll take one. So I can also integrate those up, so I just see the brightest one each. And now I'm taking pictures at about 3 frames a second. Hold it out to your side. There you go. Okay. So if I stop that, which is, there's a perfect position, and I make a 3D image of this. Here's a 3D image of it, and now in our crummy viewer, pre-Noel, 3D, skin does not reflect very well at 1.57, but the rest of the image is there. I can move it around. Now I haven't put the right perspectives on here. I can stretch it out so you get the right perspectives. I can do other things that if you really don't like him, I can measure the distance to him. He is 50.36 feet away, so I'm really tired of looking at him, so I'll set this near range for 60 feet, and he should go away. And he's gone. Okay, so there's our, you can come on back. The camera operation is really rather simple. I can adjust the sensitivity on the camera. I can adjust the amplifier gain, and I can set my range windows, and I can move my range windows around. Now this is a very complex engineering screen. It's really 3 buttons that you tweak, and you start it up and run it. The visible image that you're looking at that goes with this is a very poor camera. It's as good as you can do. It's a few years old. It's something we had because we cared about 3D. This really bad camera was what was used to create those images that Noel used. I think it's a 1024 by 1280 or something.
512 square.
It's a 512 square because we reduced the resolution. But you can imagine if you put a couple thousand by a couple thousand pixels on there, and you cleaned up the bad pixels, and you did smoothing and nearest neighbor averages and histogram equalizations, this stuff would just light up and look really good. So now that concludes our talk, and I think we're ready to entertain any questions you may have.
Turn this, take some pictures.
Oh,
Just turn this on sequence mode for here for a second.
you want me to do a sequence?
Yes.
Okay.
I'm
Might work. Pointer, do you want to point it at the crowd and see if we can see him? Looks like it'll work, huh?
over there.
Okay, you ready?
Yeah. Go.
We're going to take a quick sequence here. Go. Okay, done. So we took a quick sequence of you. Noel's going to do something with it, I think.
No, I'm not.
Oh.
You're going to play it.
I can play it back.
Do the Auto 3D.
It'll be slow, but
Yeah,
we
that's
can
okay.
see it.
They don't care.
Okay, so we can play this thing back slowly because this computer isn't Noel's. And let's see if I set that
you
for
went like 10, 15.
40.
It's the other side. Yeah, okay. All right, so run it.
And let's do, I think I have to open that up. Auto 3D, slice, play. And in the background, this will just be playing what we saw. We started over here, and we're sweeping across, and it has a hard time up real close because this wasn't designed for real close stuff, and again, I haven't stretched this out. But if I do play around with this and rotate this around, maybe zoom this back in.
It really likes running at 100 feet to 300 feet. That's a really good range.
This is about the toughest thing to do, and especially with skin up close. It's, it can be set to work better here. So again, this is still engineers building this thing. There's no producibility on it. It's all handmade. It'll be really fun on our next generation to have that whole camera fit inside of a beer can. So there, I'm ready to entertain questions.
Right is the pulse compared to, say, ambient sunlight?
How would you answer? Oh, how bright is the pulse compared to ambient sunlight? Well, that's a tough one to answer because ambient sunlight has a very broad spectrum. This is a 14 millijoule pulse. It's only 5 nanoseconds long. Compared to sunlight, it's brighter than the sun if you could see in the infrared. But it's 1.57, so it doesn't penetrate your cornea. So the energy density on your cornea is about 3 orders of magnitude, I'm guessing, lower than what the sun energy would be on the cornea of your eye.
Just at some point this might be useful to ask cars to see through fog or rain. What would happen if I imagine I'm on the freeway, there's hundreds of cars, everyone has these. Would the cameras always appear? Or?
No. The question was, if you put this on your car for obscuration or collision avoidance, what would happen if every car has one? Would they interfere? It's a very good question. One thing, we do sample pulses coming back. So we can encode those pulses. We actually have another program where it does have encoded pulses so that you could differentiate these between the cars. And also the time of interaction is very short and the intensity levels could be differentiated. But that is something that you would have to work out. There are solutions for it. But as is, there's a possibility of interaction.
Your pulse duration's on the order of 200 nanoseconds. And if you're sampling at 30 frames a second, there's a very long time between pulses.
The light's not very dense in time.
You can also shift the frequency, and you could coordinate between nearby cars to shift the frequency so that they wouldn't be interacting.
Oh, you can also shift the frequencies. I'm just repeating Roger's answer. You can also shift frequencies and have some coordination and interaction. It's something that could be dealt with.
Have you tried mining information from different views and making more complete 3D model?
That's what the 43 was, wasn't it? Or was that just the...
That was, actually, all those scenes were from one point of view. They were all just a pan. We intentionally collect, oh, he asked if we've tried mining multiple scenes to fill in the spots that are obscured. I'm all over it. That's what I do when I'm not sleeping, which doesn't happen much. So yeah, we intentionally collected 2 scenes separated by about 120 degrees on the ground, And then when we got on the roof, we collected basically the same 2 scenes at the same distance. So that should fill in just about everything. When this software is more than a week old, then we'll be on it.
How much trouble are specular reflections, bright shiny objects?
This thing really dislikes cars. Car reflectors are intended to reflect, and so those suck. Other than that, not too bad. The glassy buildings weren't a problem. Trees, amazingly, are an awful problem. We get a lot of false hits near trees.
We need it.
But
we don't have an automatic aim control, but that's something we can
every time I complain about one of these things, they say, oh yeah, that's in the next version, it's already fixed. So right now it's bad, but it gets better.
The trouble with retroreflectors is it's not so much a problem, general problem, there's a solution. What happens right now is we get that much energy density in a part of the array and it robs our power supply. Solution is a bigger power supply or other changes to the circuitry. We've solved that. We just haven't implemented it. But it's a problem for everything, a dynamic range issue like that. It will obscure things around it locally, probably always. Yes.
Do you have plans to use multiple cameras simultaneously in an interferometry array style coordination?
It's not, this isn't a coherent style of camera. So we haven't tried to do something like that, but you could actually, in theory, do what you're suggesting, to do time and to do amplitude and phase and basically get holographic information. Or the other way to think about it is it's really a tomographic type of operation. We could do that. We haven't really had an application for it, and since we're a small company, we're completely contract driven. If somebody sent us money, then that would be fun. But sorry, I didn't repeat the question was, can we do holographic or can we do interferometric type of imaging with this? Yes.
Going off of that, so what are the sort of applications that you guys have seen of this, like in the real world? Like, I'm guessing like the military or something would be like, that sort of stuff.
They're, unfortunately, except for where you're all lucky enough to work, where you generate a lot of income, I'm assuming. We're basically driven by government contracts or government grants. And right now, almost all of that is coming from SBIR type of thing or military branches of the military. So we have contracts with nearly every branch of the military. We have almost no contracts with non-military branches of the government.
As far as applications, submarine site, since this thing works underwater, you can get a 3D model around the sub pretty darn easily. Any kind of scene surveillance, you mount one of these on top of a SWAT van. When it drives up to a scene, you scan the entire area, reverse the view to the guys inside the house and see where they can't see. That's all very, very trivial.
The other applications are collision avoidance, projectile detection, basically robot vision, those types of things, and you can imagine what everybody wants to do with them. But
the motion part is pretty cool because you can actually compute trajectory and speed from 2 successive frames pretty easily. You've got 3D coordinates of the object. It's really straightforward.
And it's true 3D trajectories. It's true trajectory, not...
So most of the applications you guys are talking about, is that all the software from now on? Like being able to stitch these frames together to make a point coherent or something like that? Or is it more?
Optics.
They're both. We're continually doing hardware modifications. Form factor matters a lot, and these are very, very difficult chips to design. A lot of companies have tried to do it, and they haven't been successful. And as a result, it's very difficult to not just design the chip, but also to interface to the chip. It's not impossible, and it's easy for us because we've learned all the mistakes. But then there's all the other ancillary stuff. If I wanted to do pictures in a room like this, I would have a very different system than one that I want to put up at 20,000 feet doing remote sensing. This one actually will do 20,000 feet to about 9 feet. It doesn't do all that well here because this is way too bright and that's way too big. So I can do a really nice job in here if I needed.
If you hadn't noticed, we've got this stopped down like really, really far.
And it needs to be smaller. And so I could have a pinhole camera and do this room. So I could make a really compact system, and the laser's way oversized for here by about almost a factor of 100, 2 orders of magnitude. Question in the back?
Can you use X-rays with this?
The question is, can you use X-rays with this? That was before I started with the company, but Roger had projects to do X-ray imaging. Want to answer that?
Yeah. No, the difficulty with X-ray imaging.
Here, Roger.
Difficulty with X-ray imaging is that there aren't any real X-ray lenses, so you have to block the light, block the X-rays. So you couldn't really do X-ray imaging with this system.
The question was, how large do our 3D video files get?
We don't have a 3D video file yet. We have the data dump from the camera, which is actually all 20 slices. They collect about 1 gigabyte per minute.
Now, because we're sending down our raw data, we can reduce that by an order of magnitude by just putting the 3D algorithm into the gate array, which is, there's plenty of room in the gate array on the camera. Right now, we process it in the computer. It's because the algorithm is still in a state of flux. So that would cut that down to 100 megabytes a minute, and then we could compress that, because there's lots of redundant or empty data, to at least another factor of 2 lossless. So it gets it down there. It's still a lot of data.
In our imaging yesterday, we collected 10 gig of data.
There's a question in the middle.
How much are you devoting to better visualization? That here is still very awkward to use and seems to work well. Static image is a thing for a moving picture of a static thing, but I can work much with more advanced visualization.
The question is, have we worked much with more advanced visualization techniques? And the answer is no. The answer is the desire is to do that, but it's that's the next phase. Oh, sorry.
How did you get the pose information
Did you hear that?
We register the 2D data and take the pose from the 2D data and apply it to the 3D.
So you just matched the frames?
Yes. How do we get the pose?
How do you get the pose information? And behind that?
Small black sheet, laser, infrared camera.
They could.
Repeat the question.
The question was, to make it smaller, lighter, and cheaper, could we use, I think you asked about holographic optical elements here instead of lens materials. And they could. And it's something that we've looked into, but it's for what we're trying to do for ruggedization, things like that. This was more standard technology, and it's just not as off the shelf as this, but it's actually a very sound idea. The size. What is the size of our sensing elements? These are. Yes, it's a 128 by 128 array. The pixels are, the pitch is 100 micron pitch in both axes. All the circuitry lives behind each one of those 100 micron by 100 micron pixels with a little bit of circuitry around the edges for some conditioning. It's got 2 output amplifiers.
I was wondering what the laser pulse energy is compared to what you might get out of a solid-state laser like a CD-ROM writer.
I'm not sure what's in. I think the CD-ROM writers are microjoules per pulse, but I really don't know that.
So that's comparable to what you said.
This is 20 millijoules per pulse. About a factor of 100 over. We can do this job with a laser diode. The trouble is, with the way our chip is designed, it wants pulses from about 4 nanoseconds to 10 nanoseconds. The laser diodes that are out there either produce 2 nanoseconds or they produce hundreds of nanosecond pulses. There's nothing in that window, but in this room you certainly could do it with a single laser diode. And we're trying to figure out how to get to that solution.
Potentially the laser's very cheap.
Very cheap. Right now we use big pump laser diodes, and it's very inefficient because we're pumping a cavity, so it's only about 2% efficient wall plug efficiency. Okay, I guess that's the last of the questions. If anybody wants to come up and look at the camera, we'll be here for a little while longer. And thank you for hosting us. We appreciate it.